Okay, let me get started. To begin with, I would like to thank Professor Sushmita Das for inviting me to give this talk. It's a pleasure and honor to be able to do that. Let me get started. So, as Professor introduced very kindly, my name is Jyotsna Bapat. I am a faculty at IIIT Bangalore. IIIT Bangalore is a relatively small and new institute, obviously located in Bangalore. And compared to the NITs, our student strength is very small. Our student strength is about 1,000, and we are a de novo university, and we are a research university. And I belong to the Networking and Communication Research Lab. I just wanted to give you a quick background on IIIT, since most people may not have heard of it, since it's a small institute. So the Networking and Communication Research Lab, it is headed by Professor Debabrata Das, and we have several young faculty members who have joined us. The research areas are quite wide, and remember, I'm talking only about the Networking and Communication Research Lab here. IIIT as such deals with different areas, different aspects of IT, and our definition of IT is quite wide. Computer science, data science, even the policies that are related to IT are considered. As far as the NCRL, or the Networking and Communication Research Lab, are concerned, the various research areas are network slicing, ORAN, UAVs as base stations for 6G, as the previous lecture was about, massive MIMO, millimeter wave communication, antenna selection, and as always, the design and development of physical layer technologies for 5G and beyond, intelligent reflecting surfaces that would be looked at in 6G. And since everything right now is about AI and ML, we are also looking at the different AI and ML algorithms for the networks, and application of coding theory for low latency communication, and the security and privacy in Internet of Things radar design. Obviously, I don't work on all of these areas, but these are some of the research areas for the Networking and Communication Lab. We are also a technology innovation hub, TIH, with the focus on advanced communication systems. The goal of this is to prepare the next generation of wireless communication systems. And again, the focus of this technology hub is to develop the implementable technology. So our mandate is just not the research paper, but we are also working with several partners in academia, including and not limited to IIT Hyderabad, IIIT Naya Raipur, IIT Bhilai, IIT Roorkee, and also with several other companies, where we are looking at building a 5G base station based on Open RAN or ORAN. Looking at the different existing AI/ML wireless optimization technologies that can be deployed in 5G and beyond networks. And as I talked about, the smart and intelligent surfaces. So the projects in this has started, and as always, all of us are always looking for good research students. So I just wanted to put this front. So we are always looking for good research students for working in these areas. Okay. All right. This was a little bit about IIIT Bangalore and my small attempt to get more research students, so spreading the word about it. Again, big thank you to the audience for being here on Saturday evening, attending a talk on 5G of all things. So I'm going to, considering the amount of time I have, I'm going to keep it rather broad and at higher level. Any of you who have interest in the field and want to know more, feel free to reach out to me. My email address is available. I'll be happy to discuss this further. Okay, so I'm going to try to keep it slightly at a higher level. So when we talk about 5G, one of the things is always referred to is 5G NR or 5G new radio. So what is so new about it? All of you are extremely familiar with the different generations. You have heard different lectures or also seen different notes on it, right? So we have had 2G, 2.5G, I guess there was even 2.9G and so on. there have been significant technological improvement and increase in the application scenarios over these generations. When we talk about 2G or 2.5G, that was able to provide mobility in your voice communication. 3G was able to provide data communication in addition to voice. Over all these improvement progression, the improvement in overall quality of service as well as energy efficiency was always the goal that has always been there through. Now, 4G or LTE was a complete redesign and simplification of the 3G network architecture, resulting in significant improvement in terms of the the data rate, as well as significant reduction in transfer latency and higher efficiency and speed in the network. So 4G was looking to cater to the consumers who are looking at high data rates as well as higher mobility. Looking at most of you here, all of you wanted since you had the smartphone, you wanted to be able to browse faster. You wanted to be able to connect to be able to download different videos, to be able to upload different pictures that you were taking. While 5G was developing, at the same time, there were another set of devices were emerging. They were getting a lot of attention and people were expecting them to have a lot of applications. Those were nothing else but the so-called things from our IoT or Internet of Things. Now, the requirements of these things were different than what you were expecting from your 4G network. They did not need the high data rate, not even the mobility. What these IoT devices needed was because they were in large number, needed to be able to connect to the internet. And because most of these devices also needed to be cost effective, because they're expected to be low cost solutions. Now, most of them were connected using the tertiary local access network, but some of them still needed long range. You must be aware 4G provided a solution in terms of NB-IoT, but remember that was an add-on as such, and it wasn't really designed into the fabric of 4G. So that's where now when we are looking at 5G in the new radio, it wasn't just supposed to be an improvement over 4G. It was obviously supposed to be better than 4G in terms of the data rate, the range, the mobility, and so on. But in addition to that, it was also supposed to be able to cater to a variety of applications, the applications that were not looked at in 4G, and some of the applications that don't even exist right now, but we expect them to exist. So that was the idea behind 4G. Of course, even people who are not working in wireless are aware of 5G now because it was in news for all wrong reasons. I'm sure all of you know about the health concerns that people had. There was a case filed against it. While that wasn't considered to be too serious, there is a big class of people who still assume that 5G is going to create considerable health damage. Again, I am not going to talk about that. I'm not really qualified about that, but most of these, anytime there is new technology, there are always problems. Just a few weeks back, there were also discussion about Verizon as well as AT&T needed to delay the rollout of their base stations near the airport because everybody was worried that that will interfere with the plane's landing system. Again, that was a real problem and they actually needed to do something about that. How correct, wrong it was, again, I'm not really qualified to talk about it, but something that those of you are interested, you guys should look into. Okay. So, as I said, 4G was looking at one kind of application. So, the user who needed high data rate as well as high mobility and high QoS. Now, for 5G applications, we are looking at three key application areas. Now, I'm sure many of you are already aware of it, but let's look at it anyway. So, enhanced mobile broadband, EMBB, where we are looking at better connectivity for our mobile phones, a lot of hotspots. So we need high data rate, and it needs to be able to accommodate high user density. We also want better coverage. So this is what is also referred to as human-centric communication. So essentially it would be 4G done better, and also at a, no, just 4G done better. The other class that I referred to earlier, that is your IoT, the IoT or the Internet things, which is the massive machine type communication. My apologies for the spelling mistake there. It is machine type communication, not machine time communication. My apologies for this. Okay. So here we are looking at large number of devices. Now there are large number of devices. However, they need low data rate, and also the power requirement should be lower because we want these to have longer battery life. So, and here we are referring to the machine-centric communication. It's the second class, which is the URLLC, which has caught the attention of many people, many researchers, and because it is different, and that's where I'm going to be focusing my talk on, actually not focusing, a small part of it. So what is URLLC? And what does 5G need to do better, or what are the features in NR that will allow us to have this extremely reliable and low latency communication? The pictures that you are seeing, I have taken these from the 3GPP website. I wasn't able to write it in my footer here, but just to clarify. So if you look at this, this is the usage scenario for the IMT in 2020 and beyond. So you can see in this pyramid here, you are looking at on the top, you have enhanced mobile broadband, where what we want is the data rate. So we are looking at the data rate in terms of gigabytes. Now on the other side, extreme side to your left, you have the massive machine type communication, one of the, or MMTC. The applications could be smart city. People are talking about individual smart areas, smart buildings, or even the so-called smart planet. So here you have different devices that could be communicating, for example, different sensors, including the sensors that are measuring the pollution in different areas, which may be put upon the lampposts and so on. So these are the devices, or even your electricity meter. These are the devices which need to communicate periodically. However, there at a time, it's possible that there will be a large number of devices which may need to communicate to the base station simultaneously. When you look at your right-hand side corner, you have your URLLC. So the applications that you are looking at here, of course, the always famous, the self-driving car. You have other mission critical applications, for example, telemedicine or any operation that might be done remotely. It's being done by the robot and the surgeon is sitting in another place, or any of the industrial automation. There are other things that fall in between. For example, you have your gaming or work and play in the cloud. All those fall somewhere in between enhanced mobile, EMBB, and URLs. So we said that 5G needs to do better. So when we say better, we need to have some criteria, correct? With respect to what is it supposed to do better? Again, this is our wish list. We want everything to be there. We want the peak data rate to be very high. So the peak data rate is the maximum data rate in ideal conditions. The actual user experience data rate, which is about 95% rate across the coverage area per user, we would like it to be about 100 megabits per second in urban, suburban areas. The third one, which is the latency. Now here, remember, the latency is the contribution to the latency is just not from the radio. It is from the other aspects also, most importantly, also from the other layers, whether it is the MAC layer or the higher layers up. But in this case, we are only looking at the radio contribution to latency between the send and receive. So latency, essentially, you're talking about how long does it take from time I send to the time my user gets the whatever information that I'm sending. Mobility. Dr. Kalpana also in the previous talk talked about it. People are looking at how fast, whether it is trains or cars in which people are moving at, and during which we would like to have seamless handover. Obviously, I'm going to keep on connecting to different access point, G node Bs, but I would like that to be seamless and my quality of service should be guaranteed. How many devices per square kilometer can I accommodate? Because with everybody having different multiple devices. Energy efficiency is one of the requirements which is always going to be there. The next one, again, always a requirement, which is our spectral efficiency. Especially considering how expensive the spectrum is, the spectrum efficiency, the throughput in terms of the number of bits per second per hertz per cell. That is, and again, that's where we want everything to increase. And obviously the area traffic capacity. What is the throughput per meter square? So when we are measuring the performance of 5G or any of the classes, we are going to measure it with respect to these parameters. Again, this is another picture from 3GPP. Many of you must have seen it several times. It has been repeated, but I like the picture. It really drives the point, so I tend to use it in the talks. So the idea here is the same thing that I mentioned in words earlier. As they say, a picture is worth 1,000 words. I think this tells it much better. So you have different capabilities as they have been put here. You have total 8 of them. And we are trying to say how much better that we would like to do compared to 4G. Obviously, we want everything to be great. We want the data rate of 10 gigabits per second. We would like to have a spectral efficiency of 3x, which are going to be correlated. If you want the data rate to be that high, you would need to have high spectral efficiency. But while getting high spectral efficiency, I would also like to have high network energy efficiency. We are saying that I would also like to have high connection density, and most importantly here, take a look at this. We are looking at having low latency. So we are the earlier latency for 4G, which was 10 milliseconds. I'm looking at a latency of 1 millisecond, which is a dramatic change. The spectral efficiency, it has been increasing with better and better signal processing. Along with the spectral efficiency and increased bandwidth that is available with us, the data rates have also been increasing. And the area traffic capacity, these are also increasing, but this is a substantial change which needs to take place, wherein we are talking about the latency that we would like to reduce, that should be reduced, and not just by a small amount, dramatically. This is another spider web kind of a thing, again from the 3GPP website. So when you look at the 3 classes, obviously you can't have all at the same time. If you want to have if you want the latency to be very low, in that case, overall your mobility is, and mobility also to be high, you are going to have a little bit of trouble in terms of how much of the area capacity that you can have. If you want to have high connection density, then you are not going to be able to have high data rate. So looking at this, you have this nice spider web. So for enhanced mobile broadband, we are looking at high data rate. Again, that implies we would need higher spectral efficiency. So the important things are we want high data rate, we want high mobility, and we are always working towards high network efficiency. So for these devices, we are not really talking about having a large thousands and thousands of devices trying to connect at the same time. So connection density is not really an issue here. Versus for MMTC, we want high connection density, but I'm not really particular in terms of, and of course I want a good energy efficiency, but I'm not really particular in terms of my data rates or even mobility. I can manage with lower data rates. With URLLC, I'm looking at specifically the low latency. So how does 5G plan on doing so well? in so many different these things that were mentioned. Remember, there were about 8 criteria. How does it manage to do that? What has changed? Let's take, there are several things that are changed. I'll talk about few of these aspects. One is you are looking at a new spectrum. You are looking at the 2 frequency ranges. The first one is called FR1. Earlier, it used to be referred to as the sub-6 gigahertz range. So here, the maximum channel bandwidth defined is 100 megahertz, and the band most widely used for 5G is 3.3 to 4.2 gigahertz. The FR2 range, which falls in the millimeter waves, and which is what has gotten most people very, very worried about the impact of 5G on health. Although these frequencies don't fall into the range of ionizing frequencies, these are still non-ionizing. So the minimum channel bandwidth here is defined as ranging from 50 to 400 megahertz. As always, the higher the frequency, as we keep going higher up in the frequency, in the spectrum, we are able to get wider and wider frequency bands. And as you already know, the higher the frequency that we go, the propagation characteristics are going to get more and more hostile for the higher frequencies. So typically, you would use FR1 for the macro or micro cells, and for the small cells, you would be looking at FR2. The second one, which is one of the big change in 5G, is the incorporation of massive MIMO and beamforming. It capitalizes on 3 key concepts: the spatial diversity, spatial multiplexing, and beamforming. With the large number of antennas in massive MIMO, I know the massive and massive. Here, essentially what you have is 3D beamforming. This 3D beamforming creates the horizontal and vertical beams towards the user. So, although typical, again, as I said, when people are worried about these millimeter waveforms also, obviously the output transmitted power of 5G is higher than 4G. That is one of the reasons people were worried about it. However, when the signal travels, all of you are familiar with, even if you go with your basic free space path loss, with the increasing distance, the strength is going to come down rather rapidly. It's not really going to affect a person as such. However, people are always going to be worried about it. With this 3D beamforming creates this horizontal and vertical beam towards the user, increasing the data rate and the capacity for all the users. Those of you who have stayed in really, really high-rise buildings might have known, as you go higher up in the building, you are on the 30th or 50th floor, suddenly there is no internet connectivity. That's not going to happen with 5G. At least we hope so. Few more things that are happening with 5G. It's the network flexibility. You have a flexible physical layer and specifically the numerology. This numerology will allow different subcarrier spacing and which will help addressing the latency issues. And as I said, I'm going to keep my talk at a high level, but only one topic in which I would like to go slightly deep into, and that's the different numerologies that are used in 5G. 5G also uses network slicing, which is multiplexing of virtualized and independent logical networks on the same physical network infrastructure. Each network slice is an isolated end-to-end network tailored to fulfill diverse requirements of an application. So we are able to slice the network. Remember, these are logical slices. These are not the physical slices. And NFV and SDN are the key enablers which are used in helping in virtualizing these different applications in the network. NFV will enable network slicing, and the SDN that is going to allow us to do that. In addition to this, 5G also natively, organically supports all spectrum types. So licensed, share, unlicensed, and the 5G on the use of 5G on the unlicensed band, that's the active research area right now. Also supports different bands, frequency bands, low, mid, high, different range of deployment models. Like we're going from our traditional large macro cells, micro cells, as well as the hotspots, and also different ways in which we can connect. And these are some of the different things that 5G does, which will allow it to cater to the devices that fall under EMBB or under URLLC or under MMTC, all at the same time. Yeah. Again, if there are any questions, feel free to also put it in the chat. I'm logged on from two different systems, so I'm happy to take any questions in between also. Okay. So one of the important elements for any mobile communication system is the waveform that we use for the radio link in the radio access network. For the 5G new radio, for all its talk about being new, cyclic prefix OFDM or CPOFDM was chosen as the main candidate, and this DFT or discrete Fourier transform spread OFDM is also used in some areas. OFDM was the waveform that was also used for 4G. It has been used in Wi-Fi, whether it is 802.11g, N, or 802.11ac. So that is not exactly new, but there are some flavors or changes in the OFDM which is being used. Most of you are familiar with OFDM. OFDM provides the high spectral efficiency while giving protection against frequency selective fading without the need of an equalizer. And it also enables the multi-access capacity when we use the OFDMA. Okay, at this point, I'm going to look at very quick basics of OFDM. I said at the same time that all of you are familiar with OFDM, but the reason I'm going to go over it real quick is so that those of you who are not familiar with it or have forgotten about it, this will give you an idea about what I'm talking about in terms of the numerology and towards the latency. So OFDM falls under the class of so-called multi-carrier modulation or MCM. The idea is very simple, right? You're going to divide the bit stream that you want to transmit into different substream and send them over different subchannels. When these subchannels or the subcarriers are orthogonal under ideal propagation conditions, again, operative word here is ideal, then your multi-carrier modulation is referred to as orthogonal frequency division multiplexing or so-called OFDM. How many substreams do we choose? We are going to choose that so that each subchannel bandwidth is less than the so-called coherence bandwidth of the channel. So each subchannel is going to experience what is called as the flat fading, or wherein we are saying the intersymbol interference is relatively small. So this is one of the standard pictures you guys have seen for our multipath channels. And you know, whenever your signal is reaching the receiver via different paths, when they add together, your channel is going to be frequency selective. Now, in this case, for example, you seem to have one line of sight component, and the time taken, typically we take that standard one to be 0. So now here, the time over which the signal is arriving on the receiver is ranging from tau 1 to tau 3, and this is what we refer to as the delay spread of the channel. So any signal which is traveling through through your wireless system, it is going to expand in time as well as in frequency. The expansion in time and frequency is inevitable. However, the impact of that expansion in time, so whatever is your signal band, when it is traveling in time, it is going to expand in time, that expansion will be harmful or significant, especially when your original waveform is very narrow. Just to give you a very simple example, Let's say I have two channels here. One is 100 kilohertz bandwidth channel and one is some 200 megahertz bandwidth channel. And so in this case, your symbol period TS is nothing, is equal to 10 microseconds versus here my symbol period is going to be 10 nanoseconds. Now think about the previous picture that we had. So let's say the difference between tau 3 and tau 1, which was our delay spread, let's say it is equal to 5 microseconds. If my symbol period is 10 microseconds, this is really not going to create too much of a problem for me. So even so, although the channel looks the same, the impact is going to be much higher when your bandwidth is higher, because when my symbol period is 10 nanosecond and my delay spread is 5 microseconds, my intersymbol interference, think about it, my channel impulse response is going to be of length approximately equal to 500. That's a nasty channel, and that is going to create significant problems, significant intersymbol interference, and you are going to have very high bit error rate here. So the simple idea here is that if your TS, your symbol period is larger, or if you are sending the symbols at a slower rate, the impact of multipath is going to be much lesser for you than when you are looking at a channel which is wideband on which you are sending symbols at a much higher rate. Correct? So real quick, your coherence bandwidth is the statistical measurement of the range of frequencies over which the channel magnitude response is considered to be flat. So approximately you are saying that the two frequency within that frequency band will experience correlated fading. How much of that correlation is, whether we want 90% correlation, 50%, that's different. I'm sure all of you know about it. Any frequency selective channel typically requires an equalizer. Your frequency selective channel, essentially, think about it. This is the channel that is going to expand your signal in time domain, or this is a channel with memory. So you are going to need an equalizer which should be matched to the channel response. And the longer the channel response, higher the memory of the channel, more difficult or complex your equalizer is going to be. The more complex the equalizer, longer it takes to train the equalizer. In wireless systems, that is just not feasible. Your channel is expected to change rapidly. That means your equalizer response must be adapted equally rapidly. While processing power is not an issue, every time you need to send a training signal, you are going to waste the bandwidth because you are sending something which is already known to us. That is considerable bandwidth efficiency. So that's where our multi-carrier communication comes in. Again, this is my picture I like to see. I think it really brings out what we are trying to say. So we are trying to use the same wide band that is available to us. Remember, we are moving to higher and higher frequencies so that I have a wider frequency band available to me. So in that wider band, obviously, I want to send the symbols at very high rate. But maybe we could do the same thing. Instead of it sending it via a faucet, I could send it like a shower, wherein I am sending multiple smaller streams. Again, a quick example. Again, I have a point, folks. You might be wondering, am I teaching a class? No, I'm not, but just a quick example, okay? I'll relate it to what we are doing later. So if you think about a simple multi-carrier system where the total bandwidth is, let's say, 1 megahertz. My delay spread is 20 microseconds. So based on that, I find that my coherence bandwidth is approximately 10 kilohertz. I'm going to be very conservative, and I'm going to say that I want the channel to be really flat. So I'm going to split this into 1,000 different subchannels. So I have 1,000 subcarriers. So what's going to happen here? I have 1,000 subcarriers. That means each subchannel bandwidth is going to be 1 kilohertz. So the rate at which I'm sending symbols over each subchannel is I'm going to be sending 1 kilo symbols per second. So what I have here is my symbol period is going to be 1 millisecond. My drawing is not very good here, okay? The RMS delay spread is 20 microsecond. So that's really not going to make much of a difference, right? I'm sending a symbol 1 millisecond and a small part of it will get overlapped with the symbol which is coming prior to that. No problem. I can very easily recover from that. So now in this case, what's going to happen? I'm going to receive 1,000 symbols every 1 millisecond, which is equivalent to the symbol rate of 10 to the power 6 per second. If I was using a single carrier, now my symbol period would have been 1 microsecond and my symbol rate would have been exactly the same, which is 10 to the power 6 or 1 mega symbols per second. So by going over whether it is the faucet or the shower, the overall water that is passing through, or in this case, the overall data that is passing remains the same. So why are we talking about it here? Think about it. What is happening in single carrier is that I'm receiving one symbol every 1 microsecond versus in this case, I'm going to be receiving 1,000 symbols, but every 1 millisecond. So my latency is going to be much higher in this case. In single carrier, I have the symbols coming every 1 microsecond. Now I have a lot of symbols, but they are going to reach me every 1 millisecond. What if, okay, if 1 millisecond is not accepted, what if I reduce my number of carriers? If I reduce my number of carriers, say to 100, what is going to happen is my subchannel bandwidth is going to be equal to, instead of 1 kilohertz, it's going to be equal to 10 kilohertz. And now, while I will be receiving new symbols every 0.1 millisecond, which is going to reduce my latency. Now remember, I'm not going to be as able to deal with the hostile channels, because now it is possible by that my subchannels might see a channel which is not exactly flat fading. Remember this is exactly what we are going to be talking about when we look at our numerologies. So real quick again, so the multicarrier modulation is based on the concept of nothing else but simple frequency division multiplexing. Very old communication technology where we are transmitting multiple data streams over the common broadband medium. We have had our AM radio, FM radio, the different TV channels, everything doing that, correct? Each data stream is modulated onto multiple adjunct carriers. But we want to make sure that they are separate, that we are able to separate them properly at the receiver. If I want to listen to one radio station, I don't want to be hearing part of the other radio station. So to make sure that doesn't happen, we have something called the guard bands. And so those guard bands again means wastage of bandwidth. Again, that is not something that we really wanted. So the idea in OFDM was that if we make the carriers orthogonal to each other, so that although the different subchannels are overlapping each other in time and frequency, because of the orthogonality, we will be able to separate them. All of you are familiar with this. So when we are talking about how do we find these orthogonal carriers, for example, if you see the picture here, if sine x, that's your fundamental waveform, and sine 2x is the first harmonic, these are orthogonal to each other. However, one thing to be noted here, they are going to be orthogonal provided, what do we mean again by orthogonal? When we multiply the two and integrate the product over, that's the whole idea. What are we integrating the power over? Integrating the multiplication over. That has to be the period of the slowest waveform or the fundamental waveform, or nothing else but our first subcarrier. In this case, for example, here the period is 6. If instead of 6, if I calculated my integral from -3 to 2, the two carriers will not be orthogonal to each other. So that is an important point here. Remember, we must calculate the integral over the period of your smallest subcarrier. Keep that in mind. We are always thinking about the slowest carrier because that is going to impact on our latency. Again, I just realized my pictures are a little off. I'm sure you guys can figure out what my problem here is. So typically in LTE, the subcarriers are going to be at a distance 15 kilohertz apart. So for that, to maintain the orthogonality, the symbol duration must be inverse of that, which is 66.667 microseconds. You must have seen that many times when you are looking at standards and so on. You know where that is coming from. Why do we need that? Remember, each symbol lasts for this time, which in time domain is equivalent to multiplying your symbol with the boxcar, which is of the duration Ts. Corresponding Fourier transform of the boxcar function is nothing else but your sync pulse. Your sync pulse is not, remember, the energy goes down with the factor of by a factor of 1 over t. However, what we have in this case, we are going to have our nulls at 15 kilohertz and the multiples of 15 kilohertz, so that we are able to put our next subcarrier here at the nulls of the previous one, so that we can potentially eliminate the interference and by making these carriers orthogonal to each other. So that was the idea here, correct? So now remember, there is considerable interference. Any of you, if you look at the OFDM spectrum, for example, if you have your spectrum analyzer, just look at 2.4 gigahertz or 5 gigahertz band. It pretty much looks like white noise because when all of these add up together, it just looks like white noise. But it doesn't matter. Remember, provided we are going to retain the orthogonality, we will be able to separate the information which is sent over the carrier F1 because the contribution from all other carriers at this point is going to be equal to 0. One last thing in our recap, and then we will go to our actual topic. Okay. So we already know the mobile propagation channel is time dispersive. So although making this symbol period larger than your RMS delay spread reduces the impact of dispersion, it doesn't remove it completely. So to avoid these OFDM symbols from interfering with each other, there is something called a cyclic prefix which is introduced, which is nothing else but the redundant value of symbols for the duration of Tg, which depends upon the channel impulse response length. The reason cyclic is because, remember, the channel remembers for the duration, which is equal to Tg. So your symbol looks like it is cyclical in nature. And it does some pretty fun things. It also makes your channel matrix look circulant, whose eigenvectors are nothing else but the Fourier series. And that allows us to use the IFFT and FFT for modulation as well as demodulation. Also, one more fun thing there, it makes your linear convolution looks like circular convolution. That's why we have the cyclic prefix. Okay, we are almost at 6:30, so let me straight get on to why was I talking about OFDM, the cyclic prefix, and most importantly, the carrier spacing. Remember, going back to our URLLC, the latency and the reliability indicators for URLLC defined by ITU are, we want the minimum requirement for one-way user plane latency to be 1 millisecond. We already looked at that. And the reliability is that the success probability of transmitting a layer 2 PDU packet of 32 bytes. Remember, the packet size here is very, very small, within 1 millisecond in the channel quality coverage in the age of 99.99. So we would like it to be reliable. So your LLC is, again, it is expected to cater to multiple advanced services which are latency sensitive connected devices. Okay. So going back to this, I'm sorry. So technical specification TS 38.202 to 201 to 202, 2011 to 215 detail the physical channel and the modulation techniques that are employed by 5G frames. Most of these technologies either directly address, this is 2114, I'm sorry. The low latency communication or define approaches that support the coexistence of low latency data with other traffic conditions, commonly referred to as multi-numerology. Okay, after all this introduction, let me quickly talk about what is numerology. So what 5G does is it allows for 5 different OFDM numerologies, which is nothing else but subcarrier spacings in 5G. The first numerology, which is the 0th one, enables the coexistence with the current 4G/LTE radio, which is nothing else but, you remember, the subcarrier spacing in 4 LTE was 15 kilohertz. And the idea is that all of these can be mixed at the transmitter to give you the additional flexibility. The subcarrier spacing parameter is also related with your deployment. For example, if you are looking at a macro cell, remember you are looking at a large size cell. In that case, we want our subcarrier spacing to be as small as possible, because remember, smaller your subcarrier spacing, higher are the chances that the channel which is seen in each subcarrier is going to be a flat fading channel. When we are looking at a macro cell using millimeter wave, the travel distance is smaller. So typically your delay spread is also going to be smaller. So you may use a higher subcarrier spacing. Again, I'll show in the next slide. All these numerologies, they are all multiples of 15 kilohertz. Now remember, this is a bit of a catch-22. Whenever you have high subchannel spacing, that will give you lower latency. But however, the lower latency is going to come at a cost, because now your individual symbols are going to be a smaller length. So individual symbols are going to be smaller length in time domain. That means any delay spread is going to impact you higher. So ideally, as per Nyquist, if the ideal, you would get your best channel capacity when the number of subchannels tends towards infinity. So the larger the number of subchannels, you make them narrower and narrower, you'll have the best ability to deal with any of the channel characteristics. However, that will also result in higher latency. So what is this numerology? This is nothing else but variable subcarrier spacing that can support different use cases. Because remember, 5G is not designed just for URLLC, right? It has to support EMBB, it has to support MMTC also. So ignore this particular column for the time being. I won't be talking about it today. So the 0th numerology, that's the same as our LTE. Numeral mu equal to 1. That means your subcarrier spacing is 30 kilohertz, 60, 120, 240. 480 is also designed, but most of the times you're dealing with these three. I found this very nice picture. This is from the 5G bootcamp from the Keysight Technologies. So if you look at this, on x-axis, you are looking at the different frequencies, okay? Whether you are looking at the lower frequencies or at this end, you are looking at the very high or the millimeter wave. Now here you are looking at the cell size. As the cell size increases, you might be dealing right from hotspot all the way up to the macro cell, and the way that we are looking at latency. So if your application scenario is if you are looking at large sizes, then you are not going to be able to provide low latency or very low. Your latency is going to be medium, and your numerology that you are going to use is 0. Similarly, if you are looking at this case where you need very, very low latency, in that case, you will be able to provide that for small cells, and you can use the higher numerologies. Typically, the numerologies of 15 numerology, that is mu equal to 0, 1 and 2 are used in FR1, and the numerologies 2 and higher are used in FR2. Okay, so just quickly about the 5G frame structure. I don't want to go too much into detail with this. So what is happening here? Why are we getting these delays? Where did this 1 millisecond come from? What is so magical about it? Nothing magical per se about it. What is happening here is that the length of the radio frame is always 10 milliseconds because that's how we are processing in batches. And the length of the subframe is always 1 millisecond. That remains the same as what it was in LTE. Now, within this one subframe, the one slot is defined as 14 OFDM symbols with the normal cyclic prefix. Now, excuse me. When I use the word normal, the question might come in your mind, what is the other one? That is what is referred to as the extended cyclic prefix. Depending upon, remember, the length of the cyclic prefix ideally is designed such that the length of the cyclic prefix should be higher than the impulse response of the channel. For particularly hostile channels, you may use the cyclic extended cyclic prefix. And we also use the slight change in the cyclic prefix just so that all these boundaries are going to be aligned. So no matter what numerology that you are using, the one slot is always going to be 14 OFDM symbols. The different numerologies are going to have different number of slots within one subframe. Where am I coming here from? Let me get there in a minute, okay? The number of slots in one subframe is given by 14 times 2 to the power mu divided by 14. So, essentially for mu equal to 0, when delta F is equal to 15 kilohertz, which is same as mu equal to 0. So, the number of slots that you are going to have in one subframe is going to be equal to 14. One second, everybody. So you have your radio frame, which is of length 10 milliseconds. In this, there are going to be 10 subframes. Each will be of duration 1 millisecond. And within this, you are going to have 14 OFDM symbols per slot. Okay. So when you're with your standard with numerology mu equal to 0, which is what is used with LTE, we will have exactly 14 OFDM symbols. When with your subcarrier spacing is 30 kilohertz. Remember, you are getting wider in frequency domain. That means your symbol is going to get narrower in time domain exactly by a factor of 2. So that means you are going to have 2 slots in 1 millisecond. Sorry, I was trying to change the color, but that didn't work. Give me a second, folks. Yeah. So here I'm going to have in 1 millisecond, there are going to be 2 slots and each slot will have 14 OFDM symbols. When my subcarrier spacing is 60 kilohertz, I will have 4 slots, and again, each one of those 4 slots will have 14 OFDM symbols. So this is how it kind of looks. Let's take a look quickly. The first row is self-explanatory, and as you can imagine, when you're getting things are getting wider in frequency domain, in time domain, your symbol duration is going to become smaller and smaller. So your symbol duration is going to reduce from 66.67 microseconds to about 4.17 microseconds when your numerology mu is equal to 4. The length of the cyclic prefix again is going to reduce proportionately. Okay. One of the reasons that the way that it is reducing here is that we want to be able to match the boundaries appropriately. The idea is that the numerology mu is equal to 0 and mu is equal to 2 must be able to coexist together. The interference that might occur in between them because of any loss of or any reduction in the orthogonality is one of the active research areas. Okay, so you have the cyclic prefix. One more conclusion that you can quickly see here is that your length of cyclic prefix is reducing. That means the amount of delay spread that your system can tackle is also going down. And again, that's the reason why we were looking at this for macro cells, where your delay spread is going to be in terms of microseconds, versus when you are looking at really small cells, femtocells or picocells, your delay spread will be typically in nanoseconds, and in that case this cyclic prefix will work just fine. So your OFDM symbols, including the CP, will be equal to essentially the addition of these two, and the number of slots per frame, per subframe, as we already talked about last time, are going to go on in this fashion. So one quick homework for any one of you. Remember, in 1 millisecond, you are going to have one slot in this case. And in one slot, you are going to have 14 OFDM symbols. So this one multiplied by 14 must be equal to 1 millisecond. Take a quick look and see if that actually adds up. If it doesn't, you can figure out what is going on there. Okay, and same thing over each one of them. Now here, if this is your OFDM duration, remember the minimum schedule. So this multiplied by 14 should be approximate, should be not approximately, should be equal to 0.5, because now this will allow me to be able to schedule these together so that the boundaries exactly align. Okay. The slot duration, as you can see, the slot duration here is 1 millisecond, versus for the numerology 4, the slot duration is going to be 62.5 microseconds, and that is essentially your minimum scheduling interval. So that's what will allow us to reduce the latency. So repeating what I said earlier, every transmission slot comprises of 14 OFDM symbols. Each OFDM symbol represents an individual bit string, and with numerologies that are employing wider subcarriers, the 5G specification allows us to create mini slots from a subset. So remember earlier, each slot contained 14 OFDM symbols. 5G allows us to also create these slots with just 2 OFDM symbols, 4 OFDM symbols, or 7 OFDM symbols. And this kind of flexibility is expected to help us in scheduling the URLLC traffic along with your EMBB traffic, so that we can meet the requirements of the URLLC traffic. Remember, once the URLLC traffic comes, any URLLC request comes, you don't want it to wait. Your TTI interval is 1 millisecond. You don't want it to wait for the next TTI interval. As soon as the request comes, you want to be able to service it. Okay. The lower the transmission speed, the smaller the subcarrier spacing becomes, and fewer mini slots per slot that we can create. Okay. So I am almost at the end of my talk, quickly summarizing. So in 5G, we are able to use technologies such as flexible frame structure, the mini slots, and channel multiplexing that have been introduced in NR to reduce the latency. So your flexible frame structure, it supports different subcarrier spacings from 15 kilohertz to 240 kilohertz. Again, remember, wider the subcarrier spacing, lower will be the latency. Remembering your principles from OFDM, also remember that your channel can, your ability to face the hostile channel is also going to go down. Because of which, when your numerology is higher, typically you are going to use something like QPSK modulation. You will not really try to go anywhere at 64 QAM or something, because you already know your channel is wide, so it's likely to have some frequency selectivity present there. NR will allow you to have 1, 2, or 4 slots per subframe, and it has this flexible uplink and downlink ratio configurations. This will reduce the latency. It also allows for the mini slots. These are the times where in the time slot was your minimum scheduling unit. That was part of the reason for the latency. A slot in LTE consists of 14 symbols, where a mini slot in 5G NR can contain 2, 4, or 7 symbols. Again, while this flexibility has been given, actual implementation in terms of scheduling is going to be a bit of a nightmare there, but that is one of the research topics that some of our students are looking at right now, specifically the scheduling aspects of it. It also allows for limiting the number of retransmissions. For example, remember for EMBB, whether you are downloading the movie or when you are looking at downloading some web page, you can afford to have some latency. So the number of retransmissions allowed is higher versus for your LLC, it limits the number of retransmissions, which also takes into account so that you're not going to receive some packet really late when it is not going to be of much use. Other thing that 5G allows is multiplexing of different transmission time intervals on the same frequency. So this way we can share the spectrum without the delay. So what I was talking about is your EMBP traffic. Typically, if this is your time axis and this is your frequency axis, EMBP is going to be taking a lot of frequencies as well as for a longer time. If a URLLC traffic comes in between, remember in URLLC you're looking at short bursts of data. I mean, something as small as even 32 bytes, but I can't afford to wait. So it should be able to either you can puncture your EMBB traffic. So you're just going to stop your EMBB traffic and use that to transmit your URLLC traffic, or the other approach is wherein you are going to superimpose. And again, your URLLC traffic, depending upon the requirement, you are going to use different numerology as compared to your EMBB. Remember, even if they use the different numerologies, you can't superimpose them in time and frequency. That will cause interference. We are going to puncture the EMBB traffic and put the URLLC in that place. So those are some of the things that 5G NR is going to allow us to do, and that will help us to service different users depending upon the requirements that they are likely to have. Thank you, everybody. If you have any questions, I'll be happy to take it at this point.
Question they can ask or they can raise their hand so that.
Yes, whatever works.
Good evening, ma'am.
Good evening.
Thank you very much for your wonderful talk, ma'am. It was really informative. Ma'am, I have a question regarding the multiplexing of URLLC and EMBB. Ma'am, you have pointed out many points regarding their successful or coexistence. But if the number of URLLC users are increasing and we are using this orthogonal multiplexing or orthogonal allocation of resources, will it be okay for it, or we should consider some kind of non-orthogonal multiplexing technique along with it? So how we can make it compatible with the increasing users with the multiplexing or puncturing without degrading EMBB throughput, ma'am?
Those are some of the things that people have been looking at, but I think right now the solution that most likely that is going to work out is using this different numerology, and you need to be able to figure out, for example, if you look at some of the research paper, there is a lot of work where you're trying to decide if your EMBB traffic is getting punctured, which one should you be puncturing it, and how do you maintain the fairness. People are using different AI ML kind of techniques on that as well. But I think the bigger problem here is in terms of the alignment. For example, when you are going to puncture your EMBB traffic and you're going to tell the URLLC, the band that there has to be some signaling which is involved at the higher layers. Most of the solutions that purely look at the physical layer and don't look at what is the signaling that needs to be done. And in this case, I believe the signaling will be more of an issue. That will be rather a nightmare. So if you have the standard framework in which where you're allowed to puncture, that might be a better solution. That's what I believe, at least from what we've been working so far. Thank you. That was an excellent question. I'm happy to discuss further. If you want to talk it more, feel free to email me.
Okay, thank you so much, ma'am.
Sure. I'll type my email ID in the chat box.
Okay, Mr. Ifran Alam. So you can ask your questions.
My question is that
your voice is not audible.
Now, sir?
Little low.
Maybe you can type your question if your this thing is poor. Are they allowed to
Am I audible now, ma'am?
Yes, yes. That is they can
Am I
type.
audible?
Okay, you can ask the questions.
Am I audible, ma'am?
Yeah, I can hear you now.
Ma'am, I typed my this question also in the chat also, but I just want to ask that, like you showed on one of your slides, that about the smaller size cyclic prefixes. So, do they have any advantage over longer size cyclic prefixes?
The cyclic prefix, when you look at it, it's essentially the repetition, right?
Yes.
So when you add cyclic prefix, you are going to make your system inefficient. So we would like it to be as small as possible, but that will depend upon, remember, your channel is going to expand your OFDM symbol. And how much it expands, that will depend upon your delay spread. So based on that, your cyclic prefix length will be approximately dependent. So that's why LTE allows you, and even the 5G allows you for 2 cyclic prefix, the normal and the extended. So ideally, we want it to be not there at all.
So 5G offers this kind of advantage over 4G, ma'am, that the cyclic prefixes, is it like that?
No.
Okay.
So the cyclic prefix where you saw it was smaller for the OFDM symbol, that was for the higher numerologies.
Okay. Thank you, ma'am.
But if you see that was proportional, that's why I put the table. And I do want you to calculate, multiply that by 14 and realize that it doesn't really become equal to 1 millisecond, and then figure out why.
Roughly it was, ma'am.
I know, but roughly doesn't work, right?
Yes. Thank you.
Sure. Okay, ma'am, I have one question. Basically, the question is, suppose when we are doing the network slicing, or when we are using the NFV or SDN, so basically those SDN is using for the controlling or signaling in the control layer. So basically, when the number of devices in the 5G is increasing, when we are using or talk about the IoT, so that time the what procedure we may follow for controlling the control signal, because there is a huge overhead is going there for signaling in the control layer. So we are talking about this how we will, because there should be in the higher level. I know that as you mentioned that you are working in the physical layer. So basically above the physical layer, when you talk about the network layer, so basically the controlling is coming to the scenario. So how we can, if you have any information that we can.
This will take a little bit longer time. So Professor Suman, feel free to mail me. I'll send you one of the work that we have done in this area. So what do we exactly do when we have, actually, I'm slowly branching towards the higher layers. So especially for, what are we going to do when we have these multiple devices that are present? And the earlier question that was also asked, looking at the NOMA kind of a techniques. So most of the times we are using those during the RATCH procedures. So that although there are multiple devices that are present, we can use the sparse codes so that we can reduce the collisions and we are able to complete the RATCH.
Okay, thank you, madam.
Most welcome.